In this segment, we'll talk about how we can solve simultaneous linear equations by using the naive Gauss elimination method. So if you look at the naive Gaussian elimination method, what it simply does is that it takes simultaneous linear equations, which are the form Ax equal to c if you write them in the matrix form, and it solves it for x, which is the unknown vector. So A is the coefficient matrix, C is the right hand side vector. So once the coefficient matrix and the right hand side vector are known, you can find out what the unknown vector or the solution vector is. The naive Gaussian elimination method has two parts to it. One is, the first part is the forward elimination, and then you use back substitution. And once you do forward elimination and back substitution, you'll be able to find out what the quantity x is, which is a vector. So let's look at the forward elimination part, and it is better to look at it from an example point of view to get a feel for what forward elimination does. So let's suppose somebody gives you a set of simultaneous linear equations like this. There are three equations, three unknowns. And what the purpose of doing the forward elimination is to reduce the coefficient matrix to an upper triangular matrix. And as you can see, that since the elements below the diagonal are all zero, that makes it an upper triangular matrix. So whatever procedure you are using in order to go from here to here, it will change the coefficient matrix and it will change the right hand side vector. But the great thing about it is that why we use upper triangular matrix is because for the coefficient matrices, because if you look at the last equation, it has only one equation, one unknown, that is x3. When you look at the second last equation, it has two equations, it has one equation, two unknowns, x2 and x3, but x3 has just been found out, so that reduces to one equation, one unknown. If you look at the third last equation, or in this case, the first equation, it has three unknowns, x1, x2, x3, but you just found out x2 and x3. So you are able to find out what the value of x1 is. So bottom line is that when you are using forward elimination, it basically translates the equations into one equation, one unknown type. And who doesn't like to solve one equation, one unknown? So let's look at this. Here we have, we're going to look at the forward elimination part. We're going to rewrite our equations, which were in matrix form, in algebraic form, because it's a little bit easier to follow. That's why we are discussing the theory of the naive Gauss elimination method by using the equations in the algebraic form. It'll be n-1 steps, and you will see that why we only need n-1 steps of forward elimination when we have n equations, n unknowns. The bottom line before we go to the first step, it is to understand that let's suppose you are going to the first step of elimination. What you want to do is you want to make the coefficients of all the x1s in all of these equations to be zero. One of the ways to simply do it is to take the first equation and you divide it by a11, let's suppose, and multiply by a21. You can subtract it from the second equation, and which will make the coefficient to be zero. So that's what you continue to do for each of these equations, and hence making the coefficients of all the x1 values below the first row to be zero. So let's go and look at it step by step. So here we have what we were talking about. That hey, we're going to take the first equation, we're going to divide it by a11 and multiply by a21, which is the coefficient of x1 in the second equation. And by doing that, what we do is we get the coefficient a21 here for the first equation when you multiply it by this what is called as the multiplication factor. So what's going to happen is that if I take this equation now, which is the first equation, which has been multiplied by this multiplication factor, when I subtract from the second equation, I'll get a 0 for the quotient of x1. So that's what's going on here. This is my second equation. This is my first equation, which was multiplied by the multiplication factor of a21 divided by a11. Now if I subtract, you're going to find out that, hey, these two are going to cancel. So hence the coefficient of x1 will be 0. And the coefficients of all the other terms will change. And what we do is we denote this by A22 prime because it resides in second row, second column. But with the prime, the superscript which you're seeing here is basically to tell you that hey, it has changed. It has changed once. And that's the second row. And you continue doing this for the third, fourth, fifth, and all the way up to the nth row. So that's what I was telling you, that we got a 0 here, 0x1 here. And what's going to happen is that we're going to get 0x1 here, we're going to get 0x1 here by following the same procedure as we did for making this one to be 0. So that is the end of step 1. And let's go and see that what happens now. Now this is what we had at the end of step 1. Now what's going to happen is that you would want to use the row 2 to make these to be 0. So you can very well see that you are developing a pattern here, that you are using row 2, using element row 2, column 2 to make everything below row 2 in column 2 to be 0. And so if you are able to see this pattern, you can very well see that hey, it is easily can be programmed to be able to do that, whether you have 5 equations or whether you have 1,000 equations. So what's going to happen is that all of these will be made 0 by the same procedure as we learned in step 1. So all of these quantities are basically 0. So you have 0x2, 0x2, 0x2 going on all the way through down here. And that's the end of step 2. Now what's going to happen here is that you're going to continue this process, and you're going to take n-1 such forward elimination steps. We already showed you how to do step 1 and step 2, and that's what's going to happen. And this will be the end of step n-1. You don't need the nth step because once you have reached here, there's nothing to be made 0. That's why there are only n-1 steps as opposed to n steps. So if you look at it carefully, what you have basically done is that if you rewrite these equations in the matrix form, what you get at the end of the forward elimination steps, that you have converted the coefficient matrix into an upper triangular matrix, and then you have changes which are taking place in the right hand side vector also. If you look at this superscript here, that basically means this n-1 here. The superscript means that that particular element has changed n-1 times because it went through n-1 steps of forward elimination. However, if you look at this one here, there are only 2 primes here, which means that it has only been changed twice because it changed when you took the first step and when you took the second step of forward elimination. So again, reiterating why we do this is because let's suppose if we take this example of 3 equations, 3 unknowns, we see that hey, it has been converted into an upper triangular matrix, the coefficient matrix, and of course these numbers also change as you go through the process. But the beauty of it is that hey, you have to solve only one equation, one unknown at a time, and that's the case for when we're looking at n equations and unknowns as well. So reiterating, the back substitution will basically take the last equation, which is this one, solve for x3. It will take the second last equation, it will have x2 and x3 in it, but since x3 is known, you'll solve for x2. And here in the first equation, you'll have x1, x2, and x3, but since x2 and x3 are known, you'll solve for x1. So that's the essence of back substitution. Let's look at it from a general point of view. So in the back substitution, this is what our starting equations are. This is what we got at the end of the forward elimination steps. So if you look at the last equation, this is what the last equation is. So you can always find out what xn is by simply dividing both sides by a sub nn, and that gives xn. So how do we find out the other values of x? So this is what the xn is. So what is xi? Xi will be now going from n-1 to 1. So what's important to realize that you are first finding xn, then the next one you will be finding xn minus 1, then xn minus 2, x of 1 will be the last one which you will find. And you realize that, hey, this is the right hand side, and you subtract whatever you have to subtract in order to find x of I, Of course, you're going to divide it by the diagonal element a sub ii, but what you're seeing here is that only those elements which have already been found in the x vector are being used here. So let's suppose you are at x of I. That means that you already found out what x of n is, what x of n minus 1 is, what x of I plus 1 is, and that's why you find out only those x values right here in the right hand side of this particular equation. You can always bundle these terms together, and when you bundle these terms together, this is what you're going to get as a summation right here. So it is going to, again, if you look at the summation here, it goes from I plus 1 to n. And because those are the x quantities which you already found. You found xn, xn minus 1, all the way to xi plus 1. And that is the formula for each of xi. So you can always program that again because there's a pattern there. And that is the back substitution part. And that is the end of this segment.